Well, in standard cosmology and Big Bang physics, it's often stated that time begins at the Big Bang. There's no such thing as before the Big Bang. So why do people say that? Well, if we ignore inflation, then the standard cosmology implies that in the past, there's a space-like hypersurface on which the Hubble parameter h, defined to be a dot over a, where a is the scale factor of the universe, becomes 1 in natural units. And even if you include inflation, some people argue that there must be such a even so, there must be such a hypersurface to the past of the inflationary era. When h equals 1, that means that there is curvature on Planckian scales. And I'm going to call that hypersurface where h is 1, the Big Bang, or Big Bang hypersurface. So there, on that hypersurface, or then, if you like, the temperature, density of matter, and curvature is Planckian. But actually, interestingly, the curvature is only Planckian in the time direction. And in the space-like directions, the curvature is negligible, very small. In fact, I think something like 28 orders of magnitude smaller than the Planckian curvature in the time direction. And this is the so-called flatness problem. It's a fine-tuning problem, because why would you'd expect everything to be Planckian at the Planck era. Okay. So there's general, although not universal, agreement that the differentiable manifold structure of Lorentzian geometry is not a good description of space-time there at the Big Bang, on the Big Bang hypersurface. And there's a singularity broadly interpreted as a breakdown of known theory. And if there's no Lorentzian space-time, then there's no time, there's no before, and that leads to this statement that time begins at the Big Bang. And it's taken forward in quantum cosmology particularly by the proposal that the universe tunnels into existence from nothing to the Big Bang hypersurface, and the no boundary proposal of Hartle and Hawking for a wave function of the universe is based on this heuristic. But there are alternative pictures for cosmology, and in particular, there are what people call cyclic or bouncing or oscillating models. And this is another heuristic that's long-standing and attractive, and it's been around for a long time. And in the cyclic models, there can be finitely many cycles in the past, or infinitely many. There are cyclic models with no singularity, in which continuum space-time is always a good concept. The universe doesn't approach a singularity, but it just oscillates in scale factor. In which case, there would be no problem with the notion of before. But a more common cyclic model is one in which is punctuated by singularities. There's a Big Bang, and then there's some semi-classical epoch in which space-time is described by Lorentzian geometry. And then a collapse phase ending in a big crunch. And then quantum gravity, deep quantum regime, no continuum space-time, something, something. And then there's another Big Bang, followed by a semi-classical epoch, and then a big crunch, etc. So how do we make sense of, in these models, of the and then, in the absence of continuum space? So if this heuristic is right, and there's no continuum space-time at the singularities that are between the semi-classical epochs, how do we make sense of this concept of and then? There's no continuum space-time there. To phrase the question another way, how can one distinguish physically a cyclic model from a model in which these epochs between Big Bang and Big Crunch just sort of snip them at the singularities and just put them next to each other in space-like relationship to each other, in something more like the conventional multiverse picture. I kind of laughed to myself when I wrote conventional multiverse picture. But what does it mean that these epochs are one after the other rather than just sort of side by side? You know, they just all exist space-like to each other. Okay. The causal set approach to the problem of quantum gravity is a framework for exploring these issues. And it's particularly well suited to asking these questions, exploring these issues, because in this approach, the concept of causal order that is there in continuum spacetime and general relativity survives in the deep theory, though continuum Lorentzian spacetime does not. And the main ingredients of this approach are causal order, and also fundamental space-time discreteness and the path integral. So those are the sort of three pillars of this causal set approach to the problem of quantum gravity. And let me note here that causal order is a term that's inherited from continuum GR. And what it means is the order relation of before and after. And it doesn't imply causation, as in cause and effect, which is lucky because I don't know what that might mean. I mean, I'm glad that it doesn't imply causation because I don't know what causation means. So, but when I say causal order and causal sets, the word causal, overused word, all it means is before and after. It doesn't mean that one thing causes another thing. So this idea that causal order is a more primitive notion than time is an ancient tradition of thought. And if there is causal order in the deep theory, then it doesn't matter that Lorentzian space-time breaks down at the Big Bang. We can still understand statements that involve phrases like and then and before the Big Bang and such like. So let me give you a picture of what that might mean. Well, actually, let me tell you a bit more about causal sets before I get to a cosmological picture. So let's get a bit concrete. A causal set is a discrete partial order. And the hypothesis is that space-time in GR is a continuum approximation to a causal set. A very large causal set, our observable universe is a causal set with about 10 to the 240 elements. And that is the space-time volume of the observable universe in Planck units. Okay, so let me direct your attention to this picture here on the left-hand side, this diagram here on the left-hand side. This is an example of a causal set. It's very tiny. Nothing like our universe, clearly. It has 6 elements, and I've labeled the elements with the integers 0 through 5. And you might think of those elements actually being those integers, or you might think of those elements as being some other kind of mathematical object and being labeled by those integers. I'll come to that in a minute. So it's a set with 6 elements and a binary relation, an order relation on those elements. And that is indicated by this picture is called a Hasse diagram. And it's a diagram in which the elements are labeled by these nodes. This picture is of a graph, the nodes of the graph. And the edges are denoted by the lines, and the arrow is because the order has a direction. So in this diagram, 0 is before 1, 1 is before 3, 1 is before 5, 0 is before 2, which is before 5, and 4 is before 5. And there are other relations which are not drawn in the diagram, which are implied by the relations which are shown. So 0 is before 5, but no edges drawn because it can be it's implied by the fact that 0 precedes 2, which precedes 5. So the order relation is transitive. So that's an example of a very simple causal set. And in a Hasse diagram, the direction of the lines drawn on the page implies the order, so that after is at the top and before is at the bottom. So if I deleted the arrow, one can, and usually does, delete the arrowheads on the arrows, so that it's just the position on the page which tells you what the order relation is. So before is always below and after is always above. Okay. This example is just a finite example, and we're going to think about infinite causal sets as well. And the condition that a causal set satisfies is that it's locally finite, which means that between any two elements, there's only finitely many elements in the order. So obviously this is a finite causal set, so obviously it's locally finite. But in an infinite causal set, you can choose two elements and ask which elements are in between them in the order, which are above the lower one and below the upper one, and the answer will be just some finite number. I mentioned that we can think of these elements as actually being integers or being labeled by the integers, and I'm just going to, for definiteness, say that the ground set, what people call the ground set, the actual elements of the causal set, are going to be integers, just for concreteness. And I'm also going to adopt the convention that the order relation is compatible with the usual order of the integers. And that's also called a natural labeling. So you'll notice here that if two elements are ordered, so 1 and 5 are ordered, then the smaller integer is below the larger integer. And that's always the case. So I couldn't have labeled this top element here by 1 and this element down here by 5. That would not have been compatible with the convention that our causal sets are naturally labeled. We also adopt a principle which presumably is what underlies or gives rise to general covariance in the continuum theory. And it's the principle that the labels or the identity of the causal set elements has no physical meaning. And the only physical content of a causal set is the order relation itself. So this causal set over here is isomorphic in its order relations to this causal set over here on the right. So you can see that this element here is 1 and this is 0. So these are just different numbers. So if you like, it's a different set. Sorry, it's the same set but with different order relations on them. But they're isomorphic. There's a map between them which preserves the order. And the principle of general covariance says that this causal set is physically the same thing as this causal set. So in strictly, one is considering order isomorphism classes of causal sets as the physical entities. I want to introduce a bit of notation here, which I'll use later on, and that is minimal and maximal elements. Minimal elements have no past. So in this left-hand causal set, 0 and 4 are minimal. Maximal elements have no future, so 5 and 3 are maximal elements in this causal set.